Okay, is my screen visible?
Yes, it is visible, Abhilash.
Okay. So first we will see one problem in which we will be covering all. Let us say, take a problem and let us consider a three-phase fault as well as line-to-line fault, line-to-ground fault, and double line-to-ground fault. Let us first take the problem statement. Okay, let us draw the single line diagram. Suppose we have a generator 1 here. And then let us consider a transformer T1. And this is the bus bar 1. Bus bar 1 is connected with bus bar 2. And we also had a connection between bus bar 1 and bus bar 3. And here, this is bus bar 3. And we have another transformer at bus bar 2. Other end is connected to generator 2. Now, when we are doing this fault analysis numerical problems, it is very important to know the connection, how the transformer is connected, whether it is a star to star, primary and secondary winding, how they are connected, primary and secondary winding, star to star, star to delta, delta to star, delta to delta, star with neutral grounded to delta, delta with neutral grounded to star, star with neutral grounded and star with neutral grounded. Many connections are available. Okay, let us consider this transformer 1 is connected with star with neutral grounded on the primary side. Connection of transformer T1. Now coming to the transformer T2, let us consider it is delta one side and another side is star with neutral grounded. Even though we won't consider the connection of generator, obviously a three-phase generator, which is a synchronous generator, will also be either star with neutral grounded, or star or delta connections will be there for also generator, even though we won't focus on the connection of generator. This is nothing but the arctic resistance or rounding resistance. These are the connections of the generator and the transformers. Now, so let us see they can give the information here itself, the old values, voltage rating, MVA rating, and the per unit values they can directly give. But here, when we come to the fault analysis, the per unit values, old per unit values, I mean, when we are coming to the symmetrical fault analysis, the old per units we have seen either it is a subtransient reactance, transient reactance. But when we are coming to the unsymmetrical fault analysis, the values will be given for the positive sequence, negative sequence, and zero sequence. So let us take the values. Here, let us take the information in this problem is given in the form of a tabular column. Components, what is their base MVA? That is the old MVA value when we are for calculating the per unit values. And then what is the voltage rating, kV rating, kV, old kV, kV voltage ratings. Then instead of giving the old per unit values, they will be giving the positive sequence, negative sequence, and zero sequence. X1, X2, and x0. X0 is the zero sequence, x1 is the positive sequence, and x2 is the negative sequence. Okay, coming to here, what are all the values? What are all the components available in the single line diagram? If we see, we have two generators, two transformers, and then we have two line impedances between 1 and 2, 2 and 3, and 1 and 3. Okay, first component, let us consider generator 1. Given that the base MVA of generator 1 is 100 MVA and the kV rating of generator be 20 kV, mostly X1 and X2 will be same. The positive sequence and negative sequence impedance will be same mostly. Only the zero sequence will vary. When the positive sequence and negative sequence are same, then the positive sequence and negative sequence reactance diagrams will be same. So whenever the positive sequence and the negative sequence per unit volt per unit values are given same values, then we can do only once for positive and negative sequences. No need to do 2 times. Then coming to the generator 2. Generator 2, we are having again 100 MVA. And then they have given the kV rating as 20 kV. X1 values and X2 values again remains the same. Okay, this is 0.05. Here it is 0.15. Here also it is 0.15, and the zero sequence value is 0.05. Then what is the next component is the transformer, that is transformer 1. Transformer, we have already discussed in per unit. The voltage rating will be given for primary and secondary based on the components which are immediately connected to the transformer. We should fix the primary to secondary ratio. 20 kV by 200 kV. And coming to the X1, X2, X1, X2 and X0 values, all three are having 0.1. Similarly, for transformer T2, this is 100, and here it is 20 bar 200. If you see here, all the base MVA is 100 till now. So we can take the new values or base values are as 100 MVA, so that the per unit calculation will become simpler. Here also it is 0.1 and 0.1 here again, and 0.1 here. Then what about the remaining values? Remaining what we had? L12 or Z12, line 12 impedance. For that, here it is 100, and here it is 220 kV. And here it is 0.125. Here also 0.125. Here it is 0.3. And then we had L13. For L13, again it is 100 MVA and 220 kV. Here it is, X1 is 0.15. X2 is also 0.15. And then X0 is 0.35. We observe all the values of X1 and X2 are same. So we can only find out the positive sequence or the negative sequence. Any one sequence we can solve, so that we will get the same value for the other. We don't need to separately calculate positive and negative sequence per unit diagram, per unit values, and then reactance diagram. It will be same. Here it is 0.25. So these are the given values in the single line diagram, and then they have given for each and every component in the single line diagram what is the kV rating, what is the MVA rating, and what is the per unit values for positive sequence, negative sequence, and zero sequence. This is the case. Now, what they had asked us to find out. Here, if we see the neutral of each generator in this problem diagram, if you see here, the neutral of the generator is connected to the earth through a reactor. This here you can observe a reactor, neutral grounding earthing resistance have given. This reactor value is 0.25. Per unit. They have directly given the per unit value of the neutral to ground connected reactor for both the values, for both the generators. This is the value. Here also it is 0.2513 per unit. They have given the base value of this neutral grounding reactor. Obviously, since the generator base value from the base values from the table is 100 MVA, so the neutral grounding reactor also will be having a base of 100 MVA. Let us first of all, from the problem, let us draw the single line diagram. First step is we need to draw the single line diagram. Write all the values on 20 kV. So MVA, 100 MVA. Let us write the values here near itself. 20 kV. Here also 100 MVA, and we have 20 kV. Is corresponding to generators. And then now coming to the transformer, it is again 100 MVA both. Now the voltage rating we need to fix. Transformer 1 is 100 MVA. Again, now coming to the voltage ratings, see here, this transformer 1 is immediately connected to the generator 1, which is having a kV of 20 kV. So the primary of the transformer 1 is connected to generator 1, which is having 20 kV. So the correct order is 20 bar 2000 kV, 200 kV. The primary is connected to the generator 1. So this should match the primary rating of the transformer 1 kV rating should be nearly equal to the kV rating of the generator. So it is 20 bar.
Akhilesh, your voice is breaking.
Audible now?
Yeah, it's breaking somewhat unclear.
Hello, now am I audible?
Yeah, now it's audible.
Hello, am I audible?
Yeah, Akhilesh, now you are audible.
Okay. Now, if we see here, generator rating, we have seen 100 MVA, 20 kV, with a neutral reactance, neutral grounding reactance of 0.2513 per unit. Similarly, the same value for generator 2 also. Now, the primary of transformer 1 and the primary of transformer 2 both are connected to the generator 1 and generator 2 respectively. So, the primary rating of the transformer 1 kV rating should be nearly equal to the kV rating of the generator 1. Similarly, the primary rating of the transformer 2 should be nearly equal to the kV rating of the generator 2. So, both the transformers T1 and T2 are having a rating of 100 MVA and 20 bar 2000 kV. This is for both the transformer 1 and the transformer 2. Now, this is the first bus bar and this is the second bus bar. So, between bus bar 1 and bus bar 2, we are having this which is having a base of 100 MVA. This is having 100 MVA and voltage rating is 220 kV for all these three. 220 kV for all these three lines. That is, this is nothing but line 1 to L12 between 1 and 2. And this is nothing but between 2 and 3, second bus bar and the third bus bar, L2, 3. And here it is 1 and 3. This is L13. Okay. Now let us start solving this problem. This is the given information. Now, okay. The generators here are running no load at the rated voltage and frequency with EMFs in phase. There is no load if you observe here. Now the question is, a three-phase fault is occurred at the bus bar 3. Where is bus bar 3? Here. Here there is a fault. This is the fault point. Here there is a fault. Let us consider first case. In the first case, it is a three-phase fault. At the bus bar 3, we are having a three-phase fault or symmetrical fault. Three-phase fault is available in the first subdivision. And they had also given the fault impedance, that is ZF. Fault impedance ZF is nothing but they have given the value Z.01 per unit. Z.01 per unit. This is the fault impedance. Second subdivision, it is a line to ground fault. LG fault, again same ZF value. And the third subdivision, let us consider a line to line L to L fault with the same ZF value. And then fourth subdivision, let us consider a double line to ground fault, LLG fault. Again, the same ZF value. This three-phase fault we can also call as LLG fault. All these four are at bus bar 3. At bus bar 3. Now we need to find out the fault current for all these four cases. This is the unknown. Fault current is unknown. Okay. Now let us go for the first case. First, what we need to do? We need to draw the per unit reactance diagram. If you see here, okay, let us go to the solution. First step is we need to do the per unit analysis for given single line diagram. For single line diagram given, we need to find per unit values. Let us find out per unit. Okay, when we are finding per unit values, first let us here when we are finding per unit values, if you see, you will be having old per unit. If we want to find per unit, we need the old per unit values. Old per unit values in the given question, they have given three values. Old per unit, they have given X0, that is the zero sequence value, and they have given X1, that is the positive sequence, and they have given X2, that is the negative sequence. But if we observe, these X1 and X2 are equal. So let us solve for this is the one case we need to solve for positive and negative sequence, and this is one case. Let us solve for, first of all, let us solve for the positive and negative sequence case. That is X1, which is equals to X2. So this case first. If you see here, Generator is having 100 MVA generators, and the transformer is also having 100 MVA. All the lines is also having 100 MVA. So my base MVA is 100. I'm taking base MVA is 100 MVA, I'm assuming. Since all is having same MVA, it will be easily cancelled and it will be easy for computation. So base MVA is 100 MVA. Now what about my base KV? Since we observe, let us go for base KV. Base KV, I am assuming here in the problem. On generator, it is 20. On transformer, it will be transferred to 200 after voltage transformation. And again, here also it is 20. After transformer T2, it will be changed to from 20 to 200 since both are having same values. Then here 220. So if I take 20 kV as my base value, generator 1, generator 2, transformer 1, transformer 2, old per unit values will become new per unit values. Why? Because base MVA is same for all the components, which is equals to 100 MVA. But when coming to the old kV, if I take my new kV is equals to 20, then old kV is 20 here. So it will be simplified, and here also it is 20. After transformer 1, it will be changed to 200 kV. Here also generator 1 and generator 2 and transformer 2 old kV, new kVs are equal. So these four components per units will be equal to old per units. We only need to find the per unit values of these three line impedances. So let me take my base kV is equals to 20 kV. These two values are, I am assuming, you can take any values, but I am assuming like this so that the process will be simpler. Okay, now after finding the base, let us come to the generator 1. For generator 1, what is the formula for new per unit? Per unit new is equal to old per unit old into, what is the formula for per unit analysis? KV old divided by KV new whole square into MVA new divided by MVA old. Is this correct? Hello, am I audible? Okay. I hope I am audible. Am I audible? Hello. Okay. For generator 1, if we see the old per unit value is nothing but, for generator 1, if we see what is the old per unit value, 0.15. This is my formula. Hello, am I audible?
Yes, Akhilesh.
Generator 1. Old per unit is J.15. And then what is my KV rating? Old KV, new KV, both are 20 only, so they will cancel out. 20 by 20 whole square into, and then my MVA is 100 by 100. So it is nothing but J.15 only. Similarly, coming to the transformer generator. Okay, generator 2 also, let us find out the same thing. Generator 2 also. This is J. Okay, let us check once. For generator 2 also, it is 0.15 only, X1 and X2. J.15 into, again it is 20, only 20 kV. Old kV and new kV both are 20. So 20 by 20 whole square into 100 by 100. And then for transformer T1, this is also J.15. Coming to transformer T1. For transformer T1, okay, let us first write here. It is X1 comma X2, X1 slash X2. The meaning is this is per unit volt values. Per unit volt values is nothing but X1 slash X2, both are same. For transformer, what is the volt per unit value? It is 0.1. It is J.1 into 20 by 20 whole square into 100 by 100. Similarly, for my transformer 2 also, for transformer 1, so the old per unit and new per unit will be same. That is J.1, which is equals to J.1. Similarly, for my transformer T2 also, that is J.1 into 20 divided by 20 whole square. By 20 whole square into 100 by 100. That is again J.1. Now, okay, now coming to the line 1. Line 1 and 2, between line 1 and 2, what is the volt per unit value? Let us check what is the volt per unit value for line 1 and 2. It is 0.125. So it is J.125. J.125. After transformer T1, after this voltage transformation, if we apply, kV new will become 200. kV. Why? Because voltage transformation. We have already seen this in per unit. Voltage transformation. Previously, 20 kV is the kV new. For 20 kV, it is 20 kV. The meaning is this corresponds to the kV new value. This corresponds to kV new. And this corresponds to the primary of the transformer. Let me do here. Now, what value of the kV new will be when it comes to the secondary? Secondary kV of the transformer is 200 kV. This is the secondary. What is the corresponding kV value? This is unknown. So if we do the cross multiplication and considering it as x, then x into 20 is equal to 200 into 20. Into 20, which is meaning x is equal to 20 kV. Here, if you observe, the kV new before the transformer and the primary kV rating of transformer is same. So it is easy. Suppose if the kV new or base kV is 50 kV and the primary of the transformer is 20 kV, then you won't get 200. Here, if you see here, the kV new before the transformer, before the primary of the transformer, and the primary kV rating are same. So when you do the voltage transformation, the secondary rating of the transformer only, we are getting the answer. But if the primary rating of the transformer and the kV value, kV new before primary of the transformer are different, then you will get a different answer. What is this x? X is nothing but kV new. kV new or base kV. Or base. After T1 and T2. For both the transformer 1 and transformer 2, the ratings are same. So I am finding only one after T1 and T2. So after T1 and T2, my base is changed to 200 kV. This is the conclusion. After T1 and T2, this is the what procedure we need to follow for voltage transformation. Okay. Now, yeah, 0.25, 0.125 volt into what is my base kV? kV volt kV. What is volt kV of this L12? $220 kV. So 220 divided by what is my new kV? Just now we have calculated after transformer. It is 200 kV. Whole square into 100 by 100. Calculate this value of L12 per unit value 100 by 100. What is this value? So 20 divided by 200 is 1 or 1.1. We square 1.1, we will be getting 1.21.
0.15125.
0.15125. Okay. 15125. This is my L12 per unit value with respect to positive and negative sequence. Now let us find out for L23. L23, here it is. What is the value of L23? Here 0.25. You find out 0.25 into 220 divided by 200 whole square. J0.25 is my old per unit. J0.25 into, again here also it is 220 kV is the old kV. So 0.25 into 220 divided by 200 whole square. 200 whole square into 100 MVA. So 100 by 100. Similarly for L13, if we take, you find out this. Then for L13, what is the old per unit value for L13? 0.15. 0.15. Is J0.15 into 220 divided by 200 whole square. Into 100 by 100. Find out this also. What value we are getting if we do this? This is 1.1, 1.1 whole square is 1.21.
0.3025 Akhilesh.
J 0.3025.
3025.
3025. Okay, then what about this value? 1.15 into 1.21.
That is 0.1815.
0.1815.
Yeah.
Okay, now we have calculated 1815. Okay, now what are these values? Corresponds to positive sequence and negative sequence. Now let us also find out the per unit values of zero sequence. Then let us draw the reactance diagram for all the sequence. Now per unit volt is equals to x naught. For zero sequence I am finding. Then after finding all the per unit values, let us draw the reactance diagrams. Per unit volt is equals to x naught now. So what is my generator 1 per unit? Generator 1 per unit is equals to volt per unit of generator 1. X naught value is 0.05. So for generator 1, it is J0.05 into, again, it is 20 by 20 whole square. J0.05 into 20 by 20 whole square into, is this? Okay, correct. 20 by 20 whole square into 100 by 100. So it is J0.05. You be ready with the L13, L23 and L12 values for X naught by 100 into 100 by 100, which is nothing but the same value. That is J0.05. J0.05. Now coming to the generator 2, same generator 2, what is volt value, X naught value is 0.05 only. So for generator 2, it is again J 0.05, J 0.05 into 20 divided by 20. 20 by 20 whole square into 100 by 100. Again, it is J 0.05. Say 0.05. Now coming to the transformer 1 and transformer 2. Coming to the transformer 1, what is my X naught value if we see for transformer 1? X naught value is 0.1 and transformer 1 and 2 both is having. So it is J.1 into old kV is nothing but 20 and the new kV is also 20 by 20 whole square into my MVA. What is my MVA? 100 by 100. So it is again J.1. 100 by 100. It is J.1. Similarly, for my transformer 2 also, if we see for transformer 2 also, it is old per unit value with respect to zero sequence is nothing but J.01. So into kV is again same 20 by 20 whole square into 100 by 100. So this is again J.01. Again, as what we have seen in the previous case, after transformer 1 and transformer 2, we need to do the voltage transformation. I'm not going to repeat that. Just I will write the kV new value after transformer 1 and after transformer 2. We need to do the voltage transformation. That is voltage transformation. After voltage transformation, my new kV is nothing but voltage transformation. My new kV is nothing but 200 kV. kV new is nothing but 200. 200 kV. Okay, now what we need to do? Let us go for the line 1, 2. For L12. L12, what is my old kV, old per unit value with respect to zero sequence? That is for L12, it is 0.3. So it is J.3 into 200. Old value, old kV rating for L12 is 220. So 220 divided by 200 whole square into 100 by 100. Did you find this value? This 220 by 200 is nothing but 1.1. Square of 1.1 is 1.21. So 1.21 into 0.3 gives the answer. 1.21 into 0.3. Coming to L23, what is the zero sequence corresponding old per unit value? 0.7125. So 0.7125, J.7125. into again the same 220 by 200 whole square. Two 20 by 200 whole square into 100 by 100. What is this value? Here also it is 1.21 into 0.7125.
Akhilesh, L12 is 0.363.
0.363.
Yeah. L23 is 0.862125.
1 minute. 100 by 8. Can you repeat that?
0.862125.
Can you repeat it? 8.
862125. Your voice is breaking actually. I can't hear you. Akhilesh, your voice is breaking actually.
One three. I hope I am audible now.
Now you are audible, Akhilesh. It's 862123. Again, your voice is breaking, Akhilesh. I guess there's some connectivity issue for you.
L13 it is 0.35.
Akhilesh, your voice is breaking.
Okay.